In this screencast, I will demonstrate how to create and interpret a residual plot using CODAP. A residual plot is a visual representation that compares the independent variable with residuals created by a line of best fit. Since residuals measure the difference between the observed and predicted y value for each point, smaller residuals are desirable because that means there's less error in your predictions. Residual plots allow you to analyze whether there are patterns in the residuals. I'm going to return to the vehicles data set. Recall that we're interested in finding a model for predicting a vehicle's average city miles per gallon based on its average highway miles per gallon. Here's a scatter plot showing the relationship between these two attributes. It shows that there is a strong linear association between the variables, with a positive correlation since vehicles that have a higher miles per gallon on the highway also tend to have a higher miles per gallon in the city. To predict the city miles per gallon for a given highway miles per gallon, I will add a least squares line. The least squares line provides a linear function that models the relationship. To determine if the line adequately models the relationship in the data, we should calculate the residuals and visualize them in a residual plot. There are two ways to calculate residuals using CODAP. Recall that the residual of a data point is calculated by the y value of the observed data point minus the y value of the predicted value for the point's x value. Our data table already includes observed values, but we need to create a column of values that represent predicted values on the line of best fit. First, add a new attribute in CODAP by clicking on the plus symbol at the far right of the data table. We will name this attribute Predicted City. Click on the attribute title and select Edit Formula from the drop-down menu. Input the line of best fit given, 0.853 times highway MPG minus 3.3. Select Apply. The values shown represent the predicted city MPGs from the least squares line. To find the residual, add another attribute and name it Residual City. Choose Edit Formula and enter the difference by taking the observed city MPG minus the predicted city. This column now contains all the residuals of the data set. A second way to calculate the residuals involves CODAP automatically calculating them using a built-in function. Add a new attribute, name it Residual City 2, click on the attribute title, and select Edit Formula from the drop-down menu. Choose Insert Function, and then Statistical Functions. A number of statistical functions are available in CODAP. If you're unsure what a function means or how to use it, you can select the information icon on the right side of the menu to find out more. The function linear regression residual returns the difference between the actual response and the predicted response from a least squares line. So let's select this function. For the x variable, we will use the attribute highway MPG. You may notice that after typing one or two letters of the attribute name will appear at the bottom. For the y variable, we will use the attribute city MPG. Both attribute names should appear in pink. Since we are including all data values in our analysis, we do not need a filter, so we can delete it. Select Apply, and your residual values should now appear in this column. As you compare the two columns displaying residuals, you may see some slight differences. This is a result of the way we entered the least squares line in the first formula. The formula displayed in the scatter plot included a slope and y-intercept that were rounded, which impacts the value of the residual. It may be useful to introduce both methods for finding residuals in CODAP to students. The first method can be helpful when students are just starting to learn what residuals are. By computing the values, students may begin to understand what residuals describe. Once students become familiar with CODAP, using CODAP's linear regression residual function provides students with a more efficient method to calculate the residuals. Now that I have the values of the residuals, to create the residual plot, I create a new graph, then add highway MPG to the horizontal axis, and residual city to the vertical axis. We can resize and reposition the graph near our earlier scatter plot. There are several aspects to analyzing the residual plot to consider the quality of the linear model. First, we can examine the size of the residuals. Residuals close to zero are desirable as they indicate smaller differences between the observed and predicted values. These residuals are usually near zero, which is good. Second, we can analyze whether any patterns are visible in the residual plot. Generally, the goal of the model is to create a patternless residual plot, where the points in the residual plot are randomly scattered about the line y equals 0. If there are patterns in the residual plot, then a nonlinear model that accounts for those patterns may be better than the present one. If there are no patterns in the residual plot, that is, the residual plot shows a seemingly random arrangement of points, then the scatter and the residuals represent normal noise, or random variation in data, and the selected model is appropriate. There are no clear patterns in the residual plot, so the linear model is appropriate. Finally, we can examine if there is around the same amount of scatter throughout. In this residual plot, the amount of scatter grows larger as the highway miles per gallon increases. If we add hybrid as a legend attribute, we see that hybrids may account for this. Overall, our linear model is a good model for this data set. However, if we hide the hybrid vehicles, we create a stronger model for the non-hybrid vehicles.